Thank you, Gavin, for the introduction and the invitation to present. Actually, we are missing going to conferences, so I'm very happy to be here today. A little bit of an intro myself. I've been working in GPR technology since 2005. In 2009, I completed my PhD with a focus on 3D GPR imaging. That was back in Spain, where I'm originally from. Then I moved to Italy in 2009 and started collaborating with IDS in Europe first, and then in North America since 2013. Little bit of an intro in our company. IDS, as I said, is an Italian-based company established in the 90s. At that time, our division was mainly focused on ground-penetrating radar technology. So we became, with years, I would say, a leader in multi-channel, multi-frequency, dual-polarized ground-penetrating radar, specifically for subsurface imaging and with a main focus on utility mapping. Then in 2007, we started commercializing interferometric radar technology. That today we are also leaders in this technology applied for slope stability monitoring. And then in 2016, as Gavin was mentioning, Hexagon acquired IDS Georadar. So we are part of Hexagon, and more specifically within the Hexagon Geosystems division. Here, a quick overview of our locations and our partners' locations. I'm now speaking from the office in Golden, Colorado, and believe it or not, we got snow yesterday. So still summer, but it doesn't look like yesterday and today. Hopefully, but then the weekend is going to be better for sure. So as I mentioned previously, we work specifically with these two technologies based on both of them radar technology. I'm going to focus today more on the GPR, ground penetrating radar, and specifically also how important accurate positioning is. So including GNSS and highlighting this part, why in our industry it's so important, and also in future developments of GPR technology, I think is going to be very important. So we have a wide variety of sensors, and in ground penetrating radar, as I said previously, we focused during the first years mainly on utility detection and mapping. Also, some of our latest and greatest solutions are focused on utility mapping, and I'm going to talk about some of them and the applications on how pivotal the use of GNSS and other positioning devices is for us. But then going clockwise, here you can see we have systems for bridge deck assessment, so corrosion, concrete cover, moisture on the bridge deck, we can assess with GPR. We have systems for railway mapping. So in the sense of understanding what is the ballast fouling, moisture content. Actually, this week project in Toronto with one of our clients is finishing with this system. We also have radars for concrete imaging, archaeological mapping, and also pavement mapping. But traditionally, if you talk about GPR, you're gonna, have in mind a system like this. Like it looks like a push cart, 4-wheel, 3-wheel, 2-wheel. There are many different in the market. This, as I said, is the most common, most popular system out there. Is being used mainly for utility detection. Ideally, for utility detection, practitioners used more technology like EM locators, combining with the GPR data. And as I said, that also ideally, we try actually to push this within our users, position data with GNSS. Specifically here, hexagon solutions have the advantage of seemingly integrating all these sensors, different locators with GPR, with GNSS. A little bit of GPR fundamentals as in order to detect utilities in real time, as this is majority of the market still does that, try to locate in real time and finish the job in the field. They need to understand some basics. So here is how traditionally 2D GPR data is generated and represented. So if we push this cal, is sending these electromagnetic pulses into the ground, and our system records amplitudes of these signals when they travel through different materials. A sequence of all these amplitudes create what is called a B-scan or a radargram. And if we cross perpendicularly a pipe, we're going to see this feature that you see on this tablet PC. There is this famous, in our world, is the famous hyperbola. Everybody is talking about the hyperbolas all the time. I'll mention this word several times to see if this indicates the presence of a pipe. This is the indicator usually of a pipe, but not only, as we'll see during this presentation. Then, on the other hand, if we go on top of a pipe, like running parallelly to it, the response of the radar signal would be like a line or a layer, like is represented here, instead of a pipe. So you see that this is the first tricky thing that you have to learn as a practitioner. We have to explain if you start with this sort of entry-level single-channel GPR. As I mentioned, most of the practitioners on the utility locating try to finish in the field. So that's why they spray paint on the area where they see the pipe. And then we have reporting features, as you can see in this video. So you can prepare a quick report and pretty much finish in the field. Then you can also reanalyze the data anytime, review it and analyze it anytime. But this leads us to the first question. So how should I collect the data? Okay, so if I cross the perpendicular, I see a hyperbola. If I cross it parallelly, I see a line. What happens if I don't know if I'm crossing parallel or perpendicular? So with traditional single-channel GPR systems, there are two strategies. The first one, number one strategy would be going in randomly, so collecting random profiles, trying to cross utilities perpendicular to see these hyperbolas, and marking on the ground, spray painting, as I said. This requires either previous knowledge of the utilities orientation and or expertise, so great expertise on doing this. Then the second strategy is setting up a grid, as you can see here in option B, where you don't know where the orientation of the targets are, or maybe you are trying to not detect a pipe, but mapping a contaminant stream, and you don't know the orientation or the shape, then you can do a grid. So setting up a grid is the other, potentially the other strategy. For both options, some GPR operators use GNSS, many others just mark on the ground, and there is no GNSS information or other positional device information. Then sometimes even the contractor asks another company to go and survey those points or those spray paints, adding error to the whole process from my point of view, because this could be done, as I show in the very first video, all at once with GPR and GNSS connection when possible. We'll talk about limitations now in a minute. So from these two options, setting up the grid is usually the most accurate in terms of data positioning and efficient in terms of number of utilities detected and utilities layout. But as you can see in this video, it's time consuming. We're fast forwarding this video, because it takes some time to actually set up the grid correctly. And then the other problem with the grids is that there is no consensus on the cross-line spaces. You were seeing here how our colleague was marking with the spray those lines, like now you see, and those are the start points of each profile. And here is pretty dense, this grid, so it's good, but there is no consensus out there, as I said. So operators might try to save time doing costly space profiling, and this affects greatly to data quality and final deliverables, and can even damage a little bit the industry based on those results. Some practitioners also actually collect data in grids only in one direction also for time-saving perspective. And here, this is a good example, simple example of how you can miss important data. Here it shows scan number 1 crosses perpendicularly pipe A and B. So you can see these two hyperbolas here, very easy. Then in scan 2, it happened that pipe B turned 90 degrees. So instead of looking at the hyperbola here, it shows that this line, as I was explaining in the fundamentals. And in scan 3, pipe B is no longer here, and you are crossing parallelly to pipe A. So you see this. So this creates confusion for interpreting, and you could miss critical data. So that's why this is the main reason why we started going 3D towards 3D GPR more than 20 years ago. So instead of having just one line, the idea is having many profiles close to each other and precisely positioned. This is key. So you can look at the data as a volume and cut it in different planes. Now, the most intuitive way to visualize, let's see this place there. So I have this little video. So the operator is collecting on a grid, and then you can build this sort of, we call it, there are many ways, depth slice or tomography or C-scan. Basically what it is a horizontal slice parallel to the ground at a certain depth. You can choose the depth. In this particular case, the red lines may indicate the presence of utilities. So how could we speed up, since we see that collecting data on a grid is it takes a lot of time, so it might be look at cost savings, just not doing the grid, and this affects to the data. So we started using more antennas. So this is the precursor of the multi-channel GPR technology, and we started with the this system, the high mod, that was a modular multi-channel GPR composed from 1 up to 4 different antenna modules with different frequencies, 200 and 600. So you could speed up this process of 3D mapping. This allows you also to have this kind of data visualization that is very important during the interpretation. On the top left, upper left, you can see here this tomography view that I was explaining before. This is very intuitive, so you can see this red line very quickly that indicates one of the utilities present in this site. And then on CAT 2 and CAT 3, these are longitudinal section here and cross section. And this, for the expert user, is critical because these contain the complexity and the subtle features that can allow you to do a thorough interpretation. Then also here on this CAT, you can create like a 3D viewer that is more for a representation of the data and even deliverables. But for interpretation, these 3 CATs are really important. So if you remember on the GPR fundamentals, I was saying that we send electromagnetic pulses, like this one, then we record traces. Then we usually colorize these traces based on the values of the amplitudes. So we generate these B scans or radiograms, okay? So on these B scans or radiograms, we try to look for these hyperbolas, as I mentioned. Then, If the data is not densely sampled in all directions, utilities running in oblique orientations or other complex features like cracks, tree roots, or other unknown structures may be partially visible here on the V-scan. But what happened when I tried to see the tomography? And now here I'm just representing a point cloud of samples, points, and intensity, no interpolation of data. But just to give you an idea, here there is a lacuna on the data acquisition. There was a lacuna because we fixed it. So most of the single channel systems or practitioners of GPR were collecting very densely on the transect, on the direction that they are going, but then not on the cross direction. So this creates this low resolution data. So going to this analogy that we do with medical imaging, from a radiography to a tomography, well, the same we thought about, okay, what about the B-scan? We converted into C-scan, how we do that, how we create tomographies of the data that can show, instead of hyperbolas, I was saying, that show lines related to these pipes. Because the overall goal basically is creating clearer, crispier images, right? And here we had to do two things: create full resolution images, as I'm saying, so it's easy to understand, and also captures all the complexity of the subsurface, because it's pretty complex, the subsurface. And so no missing potential targets. And then the other one that is crucial is standardizing the data acquisition phase. So we need very dense data, and that has to be seamless for the operator. So we come up with the stream technology. With the stream technology, let's see if I can play this video here. Well, I can explain this one. So we created the stream solutions, very dense arrays of multi-frequency and dual polarized antennas that became the leading multi-channel GPR technology for utility mapping. This was a big leap. Why? Because we reduced time of data acquisition due to a bigger footprint. So now this white box contains 32 antennas, not only one. So we are covering all this footprint at once. And then we are augmenting spatial resolution due to much higher sampling. So here we have lines. We have the antennas spaced by 4 centimeters. So we are actually saving 75% of the time in the field. And then we're increasing detection capabilities because we are combining multi-antenna, multi-frequency dual polarization systems. So we only need to go in one direction and do full coverage, and that's it. This is going to give you full resolution. And this is here's a good example of the difference. So this is the, let's say, all the standards 3D images work great for an easier scenario like mapping this pipe, but what about other things? Well, this is the same data in full resolution. So the approach of a multi-channel GPR, instead of being collecting data at 2 feet or 3 feet, collecting data at 4 or 5 centimeters, and this is what you get. You get the full complexity, but you can also see all the features on the ground, or the majority of the features on the ground. So going back to those point clouds, here you can see the pipe and you can see the related pipe on the tomography. So you can see the extension, the length of the pipe. And this, again, I did it on purpose just to show the point cloud. This to me shows the power and potential of multi-channel GPR. Without even colorizing the data, just with the points and intensity, we are able to see things that you couldn't, even doing interpolation and all the other algorithms with a standard 3D. But so what we are missing? What we would have missed a lot of data if not collected with multi-channel GPR. Here, and not only utilities. Here's some examples. This is the standard 3D images that you can collect with single channel, and these are the same areas with multi-channel GPR approach. You can see here perfectly these utilities, but here you can see tree roots and even single objects that we ground truth at that time, and you can see here. Talking about tree roots, very important. They can be a big problem in urban environments. We all have been this kind of picture with, roads or sidewalks cracking because of them. They can create problems also with utilities, with buried utilities and foundations too. And distinguishing them in traditional GPR data is not easy, especially to determine their shape and length. That is really, really difficult, but also can be confusing with utilities, because like in this example, I wouldn't know even after 15 years to looking at this sort of image, what exactly is what here, and if there are tree roots, maybe these ones and these could be pipes, but it's not as certain as if I see it with full resolution images. And this is what the stream technology gives you. So you can see all these lines that are not straight lines, and they're coming from a single point and then driving from this point. So these are tree roots in urban environment, much easier to identify than with traditional 2D GPR. But this also highlights the importance of high accuracy data positioning. So if I cannot ensure centimeter precise accuracy here, and I'm mapping with coarser positioning a straight pipe, that might look like a skew pipe here, and it will look similar to a tree root. So it's for exploiting the maximum capabilities of these kind of systems, high accuracy in data positioning is pivotal. And now I'm going to go more into that here in a couple of slides. But just to show you some more amazing examples, that it's not all about utilities. We sometimes are focusing in utilities, but unknown structures are equally potentially a disruption of projects in construction. In this case, one of our clients using the StreamC mapped these buried railroads, all buried railroads, that there was no records of them, and this was only possible by using this sort of full resolution images. It would have been almost impossible to determine this with traditional GPR data. And another example is this happened a few months ago. Well, I think it was already last year in Tampa, was the discovery of this cemetery, these missing graves you might saw in the news, and this was done also with the stream technology. And it's not only about images; it's about what you can extract from those very dense point clouds of the subsurface positioned correctly. It's about qualitative and quantitative maps of bridge decks, for instance, in these examples, where you can assess on concrete cover thickness. You can infer about moisture content and corrosion. And also, I added this picture here. So it's an old project, but it's a pretty interesting one. This is a robot developed by Rutgers University under a Federal Highway Administration project. It's called the Rabbit. It's using here two of our array systems and highly accurate positioning. It has GNSS, of course. Highly accurate positioning was crucial here to assess for defects on rivers, cracks, and so on bridge decks, and also for the positioning of the robot in terms of navigation and those capabilities. Back to utilities, sometimes in GPR, due to soil conditions, like especially clay soils, it's not that easy to look for the pipe, but sometimes you have to look for other features that might allow you to see the pipe or think that there is a pipe down there. This is an example of those. And now we are looking at a 0 level. So now we are on the surface. All these white spots are manhole covers. And you can see some patches here. But if we go down in depth, and we are looking at trenches here. So the client was very happy to have this sort of imaging capabilities because he was able at least to see the trenches. And with traditional GPR, these beautiful hyperbolas were not showing, so he had to use this full resolution imaging to at least map the trenches. And again, it's not only about visualization, but having this dense sampling allows you to do things like automatic pipe detection, because you have so much data now that you can start doing developing this kind of algorithms. Another thing that is crucial here is having a software that actually is fast enough to collect, to process data of large areas. Now we are launching, and you'll see now on the next slide, systems that can go at traffic speed with 30 antennas, and now the areas are like this big. We can do pretty much entire cities. So on the software side, to have quickly fly through options, on the fly post-processing for good visualization is crucial, and we are having that now with our new software platform, IQ Maps. Then in terms of deliverables, most common ones are static images like this one that we export in 2D or 3D CAD environments, ideally in absolute coordinates coming from GNSS. There are also the possibility of doing animations of these depth slices or tomographies. So here, going from top down view, here one pipe, another pipe. This helps the user in translating the data to the final client. Here another pipe crossing, going longitudinal to this survey location. And then the most advanced would be like interpreting all that and going 3D. So this is another possibility from the software. You extract all these pipes, and then you can create this sort of simulated 3D environments that can also be exported to an augmented reality platform. Like in this case, we have in Hexagon, we have a viewer for detection. Here, of course, accuracy in data positioning is key. It's a nice feature, but the most important thing is how accurate those pipes are located. So yeah, as I'm trying to highlight in the last few slides, we need, and this is one of the limitations we have. I'm excited about this event because I'm learning a lot about new things coming, and those look very promising. We need real-time 1 centimeter precision, and it's not about positioning the data only per se, but it's for also navigation, because we need to, and I think this video will show. This is our latest development. Is the StreamUp 30 antenna array, and here you see that there's a driver. This the guy with the PC that needs to actually get the navigation properly, so you get full coverage of the area. Because otherwise, if you are leaving gaps, then you are missing basically spots that might contain features on the underground that you need. Real-time GNSS, RTK GNSS is the ideal, but it's not always possible. Why is not always possible? Well, we have it positioned here. So if we don't have the GNSS, we can use a total station. I'll show that with some examples. And we use mainly Hexagon SmartNet coverage, which is covering all these areas. So in some of the areas, we don't have coverage with SmartNet, so we have to use other services, or our users have to use other services. But then the main situation is, even in areas with with RTK service, like this is downtown Las Vegas, one of our clients using one of our stream GPR, multi-channel GPR, and here multipathing effect and limit satellite coverage can affect RTK GNSS in certain spots, and that create problems during data visualization and interpretation. Just a quick way of seeing how GNSS quality can affect GPR data. This is here, Denver downtown. Just a very simple example. These two red lines indicates two pipes going across. But if I have a problem of latency due to problems on the RTK service, then they will show up like this. So that's much more difficult for the interpreter to know if this is a problem with the latency or if actually there is no pipe here. It's just an example of how this could affect our data. How is this being solved sometimes by our users? This is a little bit old, but some of our users use total station. You can use the encoder wheel for distance, and then total station, traditional total station for a start and ending point. Or, as in this case, this was in, this is with robotic total station in Montreal. In 2014, after this sinkhole, we had to map an area of downtown Montreal, and here GNSS was not an option, and we needed robotic total station. Now, one of the problems, as you know, is line of sight. The other problem is like somebody needs to be all the time where the tripod is with the station, because people are very curious. That's a problem. Something that solves a lot of these problems is the Pegasus stream, and not sure why this video is not running, but you're probably familiar with this video. You can find it on the web. Using the Pegasus functionalities with IMU is solve many of the problems in dense urban areas. Then it's an extra cost if you use it only for positioning. Maybe it does not make sense. If you do above and below ground mapping, then it's a great solution. But there's always areas where you cannot do these kind of things, like here in the middle of a forest in a remote area in Mongolia, or here in this agricultural site. Conditions are very tough for our technology. Some people try to use also other solutions, like in this case, rotary laser. Problems are line of sight. You need to use many rotary lasers if you have obstacles, and also you need people on the tripods because of people curiosity again. Then the encoder wheel can create a slippage. Here it was solved with this rotary laser. In this case, we have a easier way to do it with two encoder wheels and the Opera Duo. So here we have two encoders, and in many of our systems we have more than one encoder, or we use a radar Doppler for measuring these distances, so avoiding these problems. We also introduce camera for assisted navigation. So this can help with your grid when you are collecting with a single channel system. And not only, this also helps with automatic pipe tracking, as we have this new algorithm on our software for post-processing. So I'm here about to end. I think I cover half an hour of my presentation. So what is next here? There seems to be no silver bullet yet. Ideally, 1 centimeter accurate GNSS data in all scenarios would be it for us. However, in the meantime, other technologies are being explored, like adding more cameras, as feature recognition, SLAM technology, inertial navigation systems, a combination of all that. It's exciting that what Eric mentioned about the real-time PPP service from Galileo. I didn't know about that, but we will need centimeter, not decimeter precision. But it sounds promising, all that. So, yeah. Thank you for the attention, and stay safe.
Thank you, Alex. Thanks for the overview of GPR, but also towards the end, you explained the two different ways that GNSS is utilized. With the like the Opera, you're getting a basic RTK position directly on it, but with like the big stream unit with the Pegasus on it, you've also got that inertial combined system in there to fill in the spots where the GNSS is not picking up. So I had a couple of questions from the audience here. What is the name of that folding triangle tool? Question.
I don't know. It's a good question. I have to ask my colleague Simon from Leica that is on that video. I'll ask him. Yeah, I don't know
Okay.
the name of that thing.
Okay, I'll make sure I post something.
But folding triangle sounds good.
All right, cool. Okay, so Jeff Z asks, you mentioned real-time automatic pipe extraction. Is that available now with IQ maps?
Yes, we are working on that. I'm not sure if it's, because I'm doing also beta testing, and so I don't know if it's already released or not, but it's on the, it's on IQ Maps. I don't know if it's released yet or not, but yeah, it's going to be, or it is already in IQ Maps, yes.
Okay, excellent. Question on the GNSS side. This came from, well, when we were pushing a Stream C around the rainy streets of Seattle, and we were on a very steep hill, and we had the GNSS up on a 6 foot, 2 meter pole. Don't want to throw you off there. And when we were on a very steep hill, I was saying, well, actually, that position is going to be a few centimeters off. Has anybody used like one of the systems with a tilt on the units, like the GS18T, the Leica?
Yeah, on the Stream C, I don't know. On the Stream EM and app, we have a customer that actually used the GS18. So, but usually on that system, maybe you don't go, unless you are mapping San Francisco or Seattle with that. I don't think they went through those steep slopes. Yeah, that's a good question. I'm also interested on seeing data with the GS18 trying to correct for that. I'm not sure if, yeah, I don't know.
It's not a tremendous amount, but I'm just wondering if that is an option now. So just speculating, if somebody wants the inertial, the inertial augmented GNSS positioning, they'd have to like put a Pegasus unit on it, or has anybody looked at perhaps just putting the Novotel span, one of those devices on it? You guys,
we have some customers playing with that, with other IMUs and trying to use a Planix or something on it. I don't have much more information about it, but yeah, theoretically, I mean, you could do it.
Okay, I'd be interested in trying that. You know how much canopy we have in our right-of-way corridors. So somebody answered the question about the folding triangle tool. It said, one example, C.H. Hansen 345 EK 90-degree aluminum folding layout square. Okay.
Okay, thank you.
Yeah, I can't cut and paste out of there and put it in the chat box, but yeah, somebody, yeah, C.H. Hansen 345 EK. Anyhow, look that up, folks, if you want to find out about it. Alex, is there anything you can tell us about what's next in?
Ooh.
Yeah,
that's a tough question to answer in public.
Okay.
Well, as I said, regarding to this presentation, I think what is next is integration with other technologies for like SLAM technology, adding these cameras, orthophotos, trying to mix some of the technologies that, I mean, the potential of Hexagon is pretty much limitless in those regards, in the sense of all the sensors that we have now, putting all the pieces together and in comprehensive projects and having a solution, that's another story. But we have some interesting projects coming up. So
right on.
I cannot say more than that.
Look forward to hearing about them. Well, thanks a lot, Alex. And I'm
Thank
going
you.
to queue up the next presentation. Up next, we're